In the last lecture, we had discussed about one form of logic, that is called propositional logic, and we have also seen how reasoning is carried out in propositional logic. Today, we will start discussions on a little more powerful form of logic called first order logic, which is also called predicate logic. This form of logic can capture more variety of sentences than can be captured with propositional logic. But before moving into the details of first order logic, let us start with the quizzes that we had given in the last class. Here is you can have a look at the statements that we had given. Mammals drink milk, man is mortal, man is a mammal, Tom is a man. These were the four sentences which were given, and you were asked to try to prove these two statements. Tom drink or Tom drinks, for grammatical part of the English, Tom drinks milk and Tom is mortal. Now, you must have seen that I am not sure how many of you succeeded in proving this given the sentences, these four sentences. But intuitively all of you can understand that mammals drink milk and man is a mammal, therefore, and Tom is a man. So, Tom drinks milk. That is obvious to common sense, but if you had tried the techniques that we had discussed like modus ponens, resolution, probably you will not be able to prove these mechanically with the information that was provided. You see, there is a subtle difference between these two statements, that I am making. One is that intuitively you are being able to understand and derive Tom drinks milk, but what is the mechanism that is going behind this reasoning? Unless we can understand that mechanism, we cannot emulate that in a computer, and because in a computer will mechanically do this. So, the mechanical methods that we had discussed like modus ponens, resolution will not be able to do that. So, what is missing? Why can't we do it mechanically, although intuitively we can understand that? We had these statements: mammals drink milk, man is mortal, man is a mammal, Tom is a man, and we are supposed to prove these. Now, mammals drink milk, if we write that in this new form, that there were some intuitive assumptions that we are making, that Tom is a mammal. So, mammal Tom, if Tom is a mammal, then drink Tom milk is true. So, you see the reasoning is possible. In order to make this reasoning possible, we had to bring in this implication sign here, and we had to write it as an implication proposition. Similarly, man is mortal, that can be written as, if Tom is a man, then Tom is mortal. This is my second implication. Man is a mammal, that can be written as, if Tom is a man, then Tom is mammal, because if Tom is a man, then Tom is mammal. This is my third statement, and Tom is a man. Now, this is no implication, this is just an assertion, Tom is a man. So, what I want to really say is that in my statement mammals drink milk, that is a statement. I can say drink mammal milk, that will be fine, but that would not help me in this particular type of reasoning, and there is also an hidden implication within this. Mammals drink milk, that means if a particular person, say Tom in this case, is a mammal, then it is also true that that particular person, that is Tom, will drink milk, all right. So, in this way if we write, then let us see how we can prove our desired statements. I am now naming these as propositions P, Q, R and S. You can see that mammal Tom implies drink Tom milk is a proposition. Similarly, man Tom implies mortal Tom is another proposition. So, all these are propositions, these are implications, and this S is just an assertion. I have also numbered them as 1, 2, 3, 4. Okay. Now, given these propositions, and if I select my favorite tool like modus ponens, if I apply modus ponens on R and S, that is man Tom implies mammal Tom is true and man Tom is true, then applying your knowledge of modus ponens, you can certainly arrive at the fact that mammal Tom. So, I can prove that Tom is a mammal. Okay. Again, if I apply modus ponens, I have derived mammal Tom, and if I apply modus ponens on this number 5 and number 1, that is if Tom is a mammal, then Tom drinks milk. Then if I apply modus ponens on P and this new one, mammal Tom, then again I can derive drink Tom milk. Thus, the desired statement that Tom drinks milk can be proven using modus ponens. Until I wrote them down as implication, I could not apply modus ponens. I could not apply the inference rule called modus ponens. Okay. Now, let us try to do the same thing using the other proof technique that we have learnt. The other proof technique was resolution, and again in resolution there is a subtle difference between modus ponens and resolution in its application. In order to apply resolution, I have to convert each of these proposition into their clausal form, and I hope you remember that a clausal form is nothing but a disjunction of literals. Okay. So, mammal Tom implies drink Tom milk can be converted to again mistake here, it should be not mammal Tom, yeah, it is all right. I have written it in a different way, mammal Tom prime, that is the same as not mammal Tom. So, not mammal Tom or drink Tom milk, I can write it in that way. And Q, man Tom implies mortal Tom. When I convert that into clausal form, that becomes man Tom not of that, that is not man Tom or mortal Tom. Similarly, the third one, man Tom implies mammal Tom, says that man Tom prime of that, not man Tom or mammal Tom. In this way, I convert each of them into clausal form. Note that this last one, Tom is a man, man Tom is itself in a clausal form. So, I need not do anything with it. Next, I have, what do I have to prove? Suppose I am taking up just only one of the statements that were given to be proven. Say I take the statement Tom drinks milk. So, the form, clausal form of that is drink Tom milk, that propositional form of that is drink Tom milk. But in resolution, what do we do? In resolution, we try to disprove, we prove by refutation. So, my starting point would be the negation of the goal, which I should try to disprove. That was the basic approach of resolution. So, here the goal is drink Tom milk. So, I convert my goal to is to disprove that Tom does not drink milk. Drink Tom milk, complement of that, not drink Tom milk means Tom does not drink milk. I have to disprove it. If I can disprove it given these statements, then I can certainly prove that Tom drinks milk. So, now let us try to do with resolution. I start with the negation of the goal. I select the one clause which has got the complement of this, and if I resolve these two, I will get a new statement mammal Tom prime, that means not mammal Tom. Now, I will have to again look into the set of statements that I have to find out which clause has got the negation of not mammal Tom, or which clause has got the literal mammal Tom. And here is one, not man Tom or mammal Tom. So, let me resolve these two. As I resolve, what would I get? Mammal Tom and not mammal Tom will resolve out, and my resolvent will be not man Tom. So, not man Tom I get. Now, I have to select the other clause that I have, man Tom. Okay. Now, as I resolve these two, what would I get? I would get the contradiction. This is a null clause. That means this goal has been disproved. Now, let me just go through this and state it in a different way. My job was to disprove that Tom drinks milk, and in order to disprove Tom drinks milk, that means in order to prove that my job was to disprove that Tom does not drink milk, I had to disprove that Tom is not a mammal, and in order to disprove that, I had to show that Tom is not a man, but Tom is a man. So, there is a contradiction, and since there is a contradiction, I am arriving at a null clause, thereby refuting my basic assumption, drink Tom milk. So, this is proven that Tom drinks milk is Tom does not drink milk is refuted, and Tom drinks milk is proven. So, we have proved the two. Similarly, for the other statement that was given in the quiz, you can try yourself and see how you can do this. Now, that was for all about propositional calculus, propositional logic. We have, I will tell you later that all through the formulation I had made a subtle adjustment. I would say that when it was written that mammals drink milk, so I have just said if Tom is a mammal, then Tom drinks milk. Well, I will show you later that was not very fair. However, we will come to that a little later. Now, I am coming to the specific objective of the things that we will learn or that we will be able to do after this specific lecture. The objective of this specific lecture is to enable you to formulate different, more variety of sentences using logic, and it will enable you to write correct predicate logic formulae. We will discuss what is predicate logic. So, for that, first let us look at the limitations of propositional logic. Why do we need another form of logic when we had propositional logic? So, the limitations of propositional logic are or will be evident from this statement. Consider the following argument that I am making. All dogs are faithful, Tommy is a dog, therefore, Tommy is faithful. Okay? That is a quite understandable argument. All dogs are faithful, Tommy is a dog, therefore, Tommy is faithful. Now, how to represent and infer this in propositional logic? Let us try. Suppose P is the proposition all dogs are faithful, okay, that stands for all dogs are faithful, and Q is a proposition that says Tommy is a dog. But can I combine all dogs are faithful, all dogs, and how do I capture, how do I know that Tommy belongs to this all dogs? So, if all dogs are faithful is true, then Tommy is also covered over there. If I had said, I mean this all dogs is covering other dogs other than Tommy. So, P and Q, can I say using this Tommy is faithful? No, we cannot infer this in propositional logic, because propositional logic here there are two different constants, two different things, Tommy and all dogs, they are different. Okay? I do not know what all dogs mean. I means maybe you and me will understand, but remember that when we are talking of logic, we are talking of a mechanical methodology that will work irrespective of my subjective interpretation. Okay? So, we have to do it mechanically. Let us see a couple of more examples. Tom is a hard-working student. I can certainly write that as hard-working Tom as a proposition. Tom is an intelligent student. I can write down intelligent Tom. If Tom is hard-working and Tom is intelligent, then Tom scores high marks. So, this is also an implication proposition, and I can write it as hard-working Tom and intelligent Tom implies that scores high marks Tom. Fine, no problem up to this. But what about John and Jill? See, here what we have said is, I have made hardworking Tom intelligent Tom, and I have written one rule that if Tom is hardworking and Tom is intelligent, then Tom scores high marks. Suppose John is another student. So, I will have to write, if John is hardworking and John is intelligent, then John scores high marks. If Jill is hardworking and Jill is intelligent, then Jill scores high marks. Do I have to enumerate for each of the students the rules separately? Is that a feasible way of doing things? And a new student works in the class, you have to know his name, his or her name, and you have to write down another rule. That is not logic. You should have a general statement to make which should apply to all these, but unfortunately, if we are restricted to propositional logic, we are restricted to this sort of statements that we can make. If we could write instead of this, if I could write all students who are hardworking and intelligent scores high marks, that would be fine. That would cover Tom, that would cover John, that would cover Jill or any student that will come in. Unfortunately, this sort of statements, all students who are hardworking and intelligent scores high marks, cannot be written in propositional logic, because in propositional logic the structure of the propositions do not allow us to do that. So, essentially when I want to write some statement like this, all students who are intelligent and hardworking, I can write that in this way: for all x, where x is a variable, you see this is white, so this is a variable, for all x such that x is a student and x is intelligent and x is hardworking. First of all x, x can be a student, x can be a teacher, x can be a visitor, but I am restricting myself to only the students. So, for all x such that x is a student and x is intelligent and x is hardworking, then x scores high marks. Now, x being a variable, I can put in a value for this variable and can make it Tom, John, Dick, Harry, Jill, whatever I like. So, what I need is the ability, is the power to write such sentences, which unfortunately was not possible in the case of propositional logic. That is why we need the predicate logic. So, essentially what was the problem? The problem is therefore the problem of infinite model. In propositional logic we have to restrict ourselves to constants, but in general propositional logic can deal with only a finite number of propositions. If there are only 3 dogs, for example, Tommy, Jimmy, Laika, for example, then I could have written T is Tommy is faithful, J, Jimmy is faithful, L, Laika is faithful. Then all dogs are faithful will be T and J and L. If there be a new dog, then and how long should we go on? That is not possible. Okay? So, that is the finiteness of the statements, and also even for Tommy, Jimmy and Laika, I have to write separate propositions and I have to do this conjunction. That is where the problem of propositional logic lies. So, what if there were infinite number of dogs? I would have faced a problem. So, therefore, we move to the new thing called first order logic. first order logic or predicate logic can be considered to be a generalization of whatever propositional logic we have understood, and it allows us to express and infer facts over in larger infinite models. For example, all men are mortal, some birds cannot fly, at least one planet has life on it. Going back to the quiz statement, all mammals drink milk, all mammals are mortal. All those statements I can do, these sort of statements I can do in predicate logic, first order logic or predicate logic, but not in propositional logic. So, what is added in first order logic? In first order logic, in addition to propositional logic, we have got the concept of variables and we have got concepts of quantifiers, which we will explain now. The syntax of first order logic, can be defined in terms of terms, predicates and quantifiers. Okay? We can express them in terms of three things: terms, predicates and quantifiers. I will explain each of them one by one now. What is a term? A term denotes some object other than the constants that we have already encountered, true or false. Okay? Tommy is a dog. Tommy is a term. All men are mortal. Men is a term. Very similar to what we talked in our propositional logic lectures, we mentioned them as objects. So, each of them is a term. Okay. Now, terms in this case can be constants as well as variables. In the case of propositional logic, it were only constants. Now, here we can see a constant of type W, any type, is a name that denotes a particular object in a set W. Let us try to understand this. When we are talking of type of objects, that is a set of objects of a particular type. Now, when I am saying a constant, then I am particularly pointing at an individual object of that set. Okay? If I say any particular variable that belongs to that set, belongs to that type, then it can connect itself to any particular object of that set. But whenever we are saying constant, then that is mapping to a particular object of that set. For example, if I say 5, 5 is an object, is a particular object in the set of integers or natural numbers. So, it is a constant. Tommy, among all the names, all the objects called dogs given their names, Tommy is a particular dog. On the other hand, a variable of type W is a name that can denote any element in the set W, any element in the set W. Okay. For example, x belongs to n, is a set of natural numbers. So, x is a particular natural number. Okay. X is a variable that can connect to any particular natural number, I am sorry. Whereas, if I said 5, then that is meaning a particular natural number. It is not meaning any element of that set of natural numbers. Similarly, D denotes the name of a dog, any dog that is in the set of dogs. So, that is the basic difference between constant and variable. Next, let us understand what is a function. A functional term of arity n, okay, how many parameters the function will have, takes n objects of type W1, W2 like that up to Wn of different types, maybe of different types as inputs, and returns an object of the type, some other type W. Now, that can be any type, all right. So, it takes parameters of objects which can be variables or constants and returns an object of a type W. Now, for example, we are familiar with these statements. function f is a function of w1, w2, wn. Plus is a function which has taken two constants, two objects of type constant, okay, from the set of natural numbers. So, this is a function. Now, so here this is the functional term, plus is the functional term, 3 and 4 are constant terms, and 7 is also a constant term. So, 7 is the value, that is the object that is returned by this function, that is returned by this function. Okay. Now, let plus be a function that takes two arguments of type natural number and returns a natural number. Now, if that be my definition, well, then let us see plus 2 3, this one plus 2 3, that is a valid function. Plus 5 plus 7 3 is also a valid function, because plus 7 3 will return an object of type natural numbers, that is 10, and then therefore, plus 5 and 10 both belonging to types natural numbers will add up and return a value of type w, that is 10, natural number 10, 15 sorry. Now, similarly plus 100, in that way I can go on writing this sort of statement. This is also a valid function, although there are a number of nested functions here. Here you see, based on my definition that I gave, that plus is a function that takes two arguments of type natural numbers and returns a natural number. Based on that definition, this is an invalid function, because minus 1 is not a natural number, and I have defined plus to be a function that takes two arguments of, both the arguments should be of type natural number and returns a natural number. Neither of these two are satisfied. Similarly, plus 1.2, 3.1, that is not a valid function based on the definition of plus, because 1.2 and 3.1 are not natural numbers, they are belonging from the real numbers. Similarly, we can have functions with variable arguments like plus xy, product prod xyz, any of these things we can have. It is not necessary, although in the examples we have shown, in the earlier example we have shown with constant, it can also have variables for that. Now, that is what is function. Probably some of you have learned that in the discrete structure course, you can consider this to be just a revision. Then what are predicates? Let us very easily understand that predicates are like functions, except that they can only return, the return type can be only true or false. These two constants can be returned. Other things are same as functions, but the return, a function can return any type of value, but here it is a little restricted, that a predicate will either be true or false. Okay. So, predicate is a function except that the return type is only true and false. Now, let us look at these examples. Greater than, GT stands for greater than xy variables is true if x is greater than y. Now, these are variables. You see, in propositional logic we could not deal with variables. Here in predicate logic, in functions we can have variables, and predicates being nothing but functions, we can have variables in predicates as well, right, and that is giving us a lot more expressive power. So, greater than xy is true if x is greater than y. If x is instantiated with a value 5 and y is instantiated with a value 10, then greater than, this entire predicate will evaluate to false, because 5 is not greater than 10. So, here greater than is a predicate symbol that is taking two arguments of type natural numbers, but it is returning a value true or false. For greater than 3 4 is a valid predicate, but greater than 3 minus 4 is not a valid predicate. Why? Because greater than is a predicate that has been defined, suppose, to take two arguments of type natural number. 4 is not a natural number, minus 4 is not a natural number. Therefore, this one is not a valid predicate. Now, validity of the predicate has got no relationship with its being evaluated true or false. A valid predicate g t x y can sometimes evaluate to true, sometimes evaluate to false, depending on what values are being given to these variables x and y. Right. Now, let us see the different types of predicates. The simplest predicate is a predicate with no variable. If we have no variable, then I will get what we had done earlier, that is a proposition. So, Tommy is a dog is a proposition, we know that, and this thing is also a predicate. So, predicate is more general. So, predicates can capture everything that proposition can, but not the other way around. So, predicate with one variable is called a property. Dog x, that is x is a dog. If x is, if and this is true if and only if x is a dog. Mortal y is true if and only if y is mortal. Okay. So, a predicate with one variable is called a property. Now, how do we formulate predicates? Let P having arguments x, y, etc., and Q having arguments x, y, etc., are two predicates. Remember how we defined well formed formula or valid sentences in case of propositional logic. We have got exactly similar type of definition in the case of predicates also. So, in predicate logic, if P and Q are two predicates, then P or Q is a valid predicate, well formed formula. P and Q is a valid predicate, not P is a valid predicate, P implies Q is a valid predicate. Exactly these similar things we had in the case of propositional logic. Okay. So, let us have some more examples. If x is a man, then x is mortal. This is a statement that I want to make. So, I can write man x implies mortal x. This is a valid predicate, it is no longer a proposition because I have got variables here. Anybody, if anybody is a man, that means any man is mortal. So, in the clausal form it will be not man x or mortal x. If n is a natural number, then n is either even or odd. Just try to do it. If n is a natural number, that means n is a variable that must be a natural number, then n is either even or odd. How do I express it? I can express it natural n, if n is a natural number, that then even n or odd n. All right. Now, even n and odd or odd n, any one of them will be true. So, in that way you can see, just let us once again look at the last example here, that looks like a complicated sentence, but as soon as we write in the form of predicate logic, and if we understand that, then it becomes really succinct. Okay. Now, we have said that predicate logic requires variables, I mean it allows you to have variables, and in addition to variables there is another thing that predicate logic has introduced, and that is called quantifiers. Now, there are two basic quantifiers in first order logic or predicate logic. For all, which is denoted as this V with a horizontal line across it. Now, for all, this is also known as universal quantifier. For example, if we say for all x, then that is I am talking of all, for any value that x can take, the proposition will be true. Another one is there exists, which is meaning which is also called existential quantifier, that something is existing. Okay. There is a subtle difference again between these two. So, for all x, suppose think of a set, let us just think of a set. All right. Let us try to do this. Suppose I have got a set, and in that set I have got a number of elements, all right. Now, when I write for all x, something is true, I write p x. That is that p x, I just say that p x is true for all x. Now, just I mean these are not, this need not be denoted as x's, I can just put thick dots here, this has got nothing to do with, these are just elements of this set. When I write this, then what I mean is that this p x will be true for any element that I choose from this set, all right. Now, suppose let me choose another color here, and I am marking some, or might be this is not very visible. Let me take this color, I mark them with this. There are some special elements, and I write, suppose I write there exists x such that q x, all right. That means this q x should be true, there should be at least one element in this set for which q x is true. Now, here I have shown that for these two elements q x is true, all right. Let me just write down an example. There exists x such that holiday x, okay. Now, if 1, 2, 3, 4, 5, 6, let me put in another one. Suppose these are the 7 days in a week. Now, is this statement true? There must be an element in this set, suppose this is the days of the week. Now, obviously, here lies Saturday and Sunday, 2 days for which holiday x is true. Therefore, there exists an x, there exists a day for which holiday x is true. At least one would have sufficed. Suppose Saturday is not a holiday, okay, only Sunday is a holiday. So, this one is not a holiday, this is just an ordinary dot, but at least I have got one, then this statement will be true. This entire predicate will be true only if this entire thing, I mean if there is at least one x. On the other hand, in order that this statement is true, all these elements in this set must satisfy p x. That is the basic difference, all right. I don't know what is happening. So that is the essential difference between existential quantifier and universal quantifier. Now, let us look at some more universal quantifiers. All dogs are faithful. Now, I write that x is faithful is being denoted as faithful x, x is a dog is being denoted by dog x. So, I can write for all x, for all dog in that set, for all dog, dog x implies faithful x, and that is true for any x which will make dog x true. That means, for any dog, any x, that is for any x that is a dog, this faithful x will be true. Now, how can you do this? The next statement, all birds cannot fly. Suppose we decide that with fly x will denote x can fly, and x is a bird is denoted by bird x. All birds cannot fly. Therefore, it is not the case that for all x bird x implies fly x. Forget about this not part right now, forget about this. In that case, if I had written this, for all x, if x is a bird, then x can fly. Now, that is not true. I am saying all birds cannot fly. So, this statement is not this entire statement for all x barred x implies fly x is not true. So, this is the implication, this is the expression for this statement, predicate logic expression with quantifier and variable for this statement, all birds cannot fly. Now, let us quickly revisit the quiz that we had done, and I said that I played a little trick, I did a little bit of adjustment. The statements which were given were mammals drink milk, man is mortal, man is a mammal, Tom is a man, these were given, and I had written them as mammal Tom implies drink Tom milk, like that. But this statement is unfortunately not a statement made for Tom alone. So, I should write it in a little different way. How should I write it? I can write it in this way now. Now, I know predicate calculus. So, why should I do that sort of adjustment that I did? So, I can write for all x, mammal x implies drink x milk. Note here, milk is a constant object. Among all the food, milk is 1. X is a variable. So, for all x, mammal x, if x is a mammal, I take one animal and see whether that is a mammal. If that is the case, then x will drink milk. Man is mortal. For all x, if x is a man, then it is mortal x. Man is a mammal. Here I should write, I should write for all x here. Here I should have written for all x. So, I should select here I should have written for all x with some color. All right, this was a mistake here. So, it should be for all x, man x, mammal x, and Tom is a man is Tom is a man was as before man Tom, there was no problem with that at all. So, now you see we can do it in a much easier way, much more natural way instead of making adjustments, and that is the power that predicate logic has given us. Okay. Now, let us look a little bit those examples I could have done, these examples right now, the universal quantifier was sufficient to deal with. Now, let us look at existential quantifier. If I make a statement at least one planet has life on it, that means here I say planet x will denote x is a planet, has life x will denote x has life on it, then my statement would be there exists an x such that planet x and has life x. That means there exists, there must be one planet, there must be one element of that set of planets, at least one, such that it is a planet and it has got life. All right. So, this is where I need universal quantifier would not do. If I had written here for all x, planet x and has life x, then this would be true only if all planets have life. No, that is not what I want to do. What I want to do is to show, to find whether there is at least one planet which has got life. Okay. I am not going into stars, I am just going into planets. That is why I put in this predicate planet x. Now, another one, say statement is like this: all birds cannot fly. All birds cannot fly. This statement is just equivalent to the statement there exists at least a bird which cannot fly. If you say, well, all birds cannot fly, I say, okay, go ahead, prove it. And you can prove it just by selecting at least one bird, might be ostrich, and you can show that, here, see, here is a bird, but it cannot fly. So, what you need to really say is there exists a bird, which cannot fly, or I can say there exists an x such that x is a bird and x cannot fly. So, we can straightway say all birds cannot fly, that is equivalent to bidirectional implication, that is equivalent to there exists a bird that cannot fly, that is there exists an x such that x is a bird and not fly x. Both these things are true for this, for a particular x at least. In that case, I can prove that well all birds cannot fly, right. Now, let us look at another interesting aspect, that is called the duality of quantifiers. There is a duality between this existential quantifier and universal quantifier. You must have observed that duality if you have noted that in this earlier example, all birds cannot fly. There is a duality. I am saying all, but I am translating that into some sort of an existential statement. Now, say if we have all men are mortal, that is equivalent to no man is immortal, similar to De Morgan's double negation, no man is immortal. Now, formally we can say for all x, men x, this is a notation for a particular type. For all x, men x implies mortal x. That means that is equivalent to there does not exist an x such that men x and not mortal x. So, I can always do that. Similarly, there exist birds that can fly. I can always make the statement like this: it is not the case that all birds cannot fly. Now, try to read it a little carefully. There exist birds that can fly. There exist birds that can fly. Again, going back to the earlier type of thing, if I have a set here, if I have a set here like this, in which there are elements, and my statement was it is not the case that all birds cannot fly, then it is again sufficient for me to show one particular element, and show that it can fly. So, there exists an x that can fly. Okay. So, there exist birds that can fly, one is sufficient. That means, it is not the case that all birds cannot fly. Now, how do we express that? Formally, there exists a bird which can fly. If I can prove that, then I can certainly prove that for all x, birds cannot fly is not true. So, that shows the duality of such statements. Universal quantifiers can again be expressed in a different way with existential quantifiers. We can do that. Now, we can go ahead with sentences and okay. Now, let us just do this. A predicate is a sentence. Any predicate is a sentence. If SEN is a sentence, then SEN's complement is a sentence. Okay. And x is a variable, then within parenthesis this sentence is a sentence, complement of a sentence is a sentence. There exists x, sentence is a sentence. For all x, sentence is a sentence. Sentence and all sentences connected with and or implication are sentences. This is and nothing else is a sentence. Now, if you recall what we discussed in the case of propositional calculus, we had also given a sort of such strict definition for what is a well formed formula. We had given that, and that is we had given a couple of examples, and so in some sort of hard definitions. We will come to these points later. Now, before that, let us look at a couple of exercises. Now, predicate logic will require a couple of more lectures to cover all the points, but let us quickly first see what we have learned today. We have seen that in the case of predicate logic is an extension of propositional logic, more powerful version of propositional logic, with the incorporation of variable and with the incorporation of quantifiers. Therefore, with these incorporations, we can capture sentences much more naturally, which we could not, either we could not capture in propositional logic, or we had to play tricks and do some artificial maneuvering to capture those, as I did in the first solution of the quiz. But as soon as we have got the power of predicate logic, we can do that. And what are the two types of quantifiers? The two types of quantifiers that we have are universal quantifier and existential quantifier. Fine. Now, again there is a duality between these quantifiers. Now, closing the whole thing with, see, recall that in the case of propositions, we said if P is a proposition and Q is a proposition, then P, and if P is a proposition, then what was the compound proposition? P or Q. Not P is a proposition. P within parenthesis is a proposition. P or Q is a proposition. P and Q is a proposition. P implies Q is a proposition. Nothing else is a proposition. That is what we did. Now, in the case of predicates, we also said that if P is a predicate, so and Q is a predicate, then so is not P, that is also a predicate. Then for all x, P is a predicate. There exists x, P is a predicate. Okay? Any predicate implying another predicate is a predicate. Predicate within parenthesis is a predicate. Nothing else is a predicate. So now, propositional logic and predicate logic, we can put them side by side and see the similarity, and also we have to observe the extra power that we have got in the case of predicate logic because of the incorporation of variables and quantifiers. Now, quickly let us have a couple of examples or exercise that you should try. Let us take some sentences which you should convert in the form of propositional logic, which you should convert in the form of predicate logic. Some dogs bark. All dogs have 4 legs. Some dogs bark. All dogs have 4 legs. All barking dogs are irritating. No dogs purr. Fathers are male parents with children. Tricky, a little tricky, but interesting. Fathers are male parents with children. Students are people who are enrolled in courses. Students are people who are enrolled in courses. Okay? So, please take them down, and these are some of the exercises which you can try to do, and in the next class we will come back to this point. We will assume that the basic definition and writing predicates will be clear through these examples that you do, and again in the next class we will look more into predicates, and specifically we will see how we can perform inferencing with predicates. Thank you.